This video is about a problem, question 1 from pre-class questions for class number 37. So a lot of you expressed that you were having some problems with this one and some of the other problems, so I thought I would help you out a little bit with this one. So here's question 1. Let's kind of go through it and see what it's asking. So the gas phase reaction for the production of PCl5 from PCl3 and Cl2 at 250 degrees has an equilibrium constant Kp of 24.2. It says consider the reverse process, the decomposition of PCl5 to PCl3 and Cl2. Okay, so this first reaction we are looking at making PCl5 from PCl3 and PCl2. Now it tells us that we're going to consider the reverse process. So now we're going to start with PCl5. It's going to decompose into PCl3 and chlorine, Cl2, at the same temperature of 250 degrees. So it says if the initial pressure of PCl5 in a reaction vessel is 1.4 atmospheres, what are the partial pressures when equilibrium is achieved? So we want to know what are the equilibrium partial pressures in atmospheres of each of these substances, PCl5, PCl3, and PCl2. Okay, let's go to our blackboard and write down some of this information. It's always the first step in solving a problem, is kind of write down, think about what you're looking for, and see where to go from there. Okay, so here's some of what we know from this problem. So I've written it down already from class 37 PCQ number 1. So this is the formation reaction that we were given, PCl3 reacting with PCl2 to form PCl5. I called it a formation reaction, not technically that. Anyway, this is at a temperature of 250, and we were given the value of the equilibrium constant K sub P. So I've written out here the equilibrium constant expression, so it's products over reactants, and since this is Kp, we're expressing amounts in terms of partial pressures. So it's the partial pressure of PCl5 divided by the partial pressure of PCl3 times the partial pressure of chlorine, Cl2, and that equals 24.2. But we're told in the problem to consider the reverse reaction, the decomposition of PCl5. So we start here with PCl5 decomposing to PCl3 and Cl2. And so that equilibrium constant would be written this way. Now, comparing the equilibrium constant that's here to the one directly above it, we see that they're just the inverse of each other. So for this reverse reaction, we can figure out the value of that equilibrium constant just by taking the inverse of that first reaction, right? So that's one of our properties of equilibrium constants that we learned about. When you reverse a reaction, you simply take the inverse of the equilibrium constant to find the value of the equilibrium constant for that new reaction. And the other piece of information that we were given is we were told that the initial pressure of PCl5 is 1.4 atmospheres. So the way to approach solving this equilibrium problem, or really any equilibrium problem, is to use that tool that we call an ICE table, or sometimes a RICE table. So RICE for reaction that you write at the beginning, and then we write I for initial, change for equilibrium, C for change, and E for equilibrium. Getting ahead of myself there. Okay, now what we need to do is try and fill in this table. So we write down as much of the information as we know. So we were told that if the initial pressure in the reaction vessel of PCl5 is 1.4, so presumably we're starting out with 1.4 atmospheres. Now, this table, technically a chemical reaction is always written in terms of counts, numbers of moles or numbers of molecules. So this means 1 mole of PCl5 is in equilibrium with 1 mole of PCl3 and 1 mole of Cl2. So our ICE table should technically be in terms of moles. But in reality, we can use any measurement that is directly proportional to number of moles. So we typically either use molarity, which is just moles divided by liters, or we use partial pressure. And remember from our ideal gas equation that pressure is equal to number of moles times R, the gas constant, times the Kelvin temperature, divided by volume. And so if RT and V are all constant, then pressure is directly proportional to number of moles. So in our problem, our Kp is written in terms of partial pressures. So we can use partial pressures because it is directly proportional to number of moles as a stand-in, a proxy for number of moles. So here in my ICE table, instead of using moles or molarity, I'm going to use atmospheres. And that's really what I want here in this last line. I want to know what are the equilibrium partial pressures, because that's what I'm going to substitute into my equilibrium constant expression, Kp, up here. So let's write down what we know. So we know initially we have 1.40 atmospheres of PCl5, and presumably we haven't had this reaction occur yet, so we've got 0 atmospheres of PCl3 and Cl2. Now what we're going to do is figure out the change. Now we don't know what the change is, but we know to get to equilibrium we're going to have to generate at least a little bit of the products because we've got none to start with. So I'm going to lose some of this PCl5. Now since the coefficient out here is 1, I'm going to lose 1 times x. Now I don't yet know what x is going to be, but I'm just going to leave it as x. So if I lose 1 mole of PCl5, if I lose x moles of PCl5, then I'm going to make x moles of PCl3 over here. So I'm going to write plus x over here. Now I said moles because remember chemical reaction is in terms of moles, but remember we're using this fact that moles is proportional to partial pressure. So these are all going to have units of atmospheres, partial pressures. So if I make x moles, x atmospheres of PCl3, I'm going to have to make x atmospheres of chlorine gas as well. And then what I do is just do the math, add down the column, 1.40 minus x, 0 plus x is x, 0 plus x is x. So these are my equilibrium concentrations in terms of x. So that's what I'm looking for. So I want these. So the answer to my question is to figure out all 3 of these. So in order to do that, I need to know what x is. So to do that, I'm going to use this equilibrium constant expression that's right here. So I'm going to scroll down, give us some more space. So I'm going to take my Kp expression that I circled up here, right there, and I'm just going to substitute in. So remember that those partial pressures are equilibrium partial pressures. So what is the partial pressure of PCl3? Well, we don't know what it is, but it's x, so I substitute that in. So what's the equilibrium partial pressure of Cl2? Well, again, I don't know what it is, but it's x, so I substitute that in. And what is the equilibrium partial pressure of PCl5? It's 1.40 minus x. All right, and that's going to be equal to the equilibrium constant value, which is 1 divided by 24.2, and I could do the math on that, and it is 0.0413. So this number is less than 1. So remember our properties of the equilibrium constant. When the equilibrium constant is less than 1, that tells us that it favors the reactants. So we're going to have a little bit of this PCl5 decompose, but not very much. So x is probably going to be small. Now, you know that we can simplify the math here a little bit. So let's think about what we have going on here. If I multiply x times x, I have x squared divided by 1.40 minus x. And that's supposed to equal 0.0413. So this is one equation in one unknown, x. And I need to solve for x. So if x is small, then I can simplify my math a little bit. So what do I mean small? Small is always relative to something, right? So smaller than this, smaller than that. So in this case, x needs to be smaller than 1.40. So we can kind of compare it to this number. So one very crude rule that you learned in one of our videos is that rule of 100. So what we do is we take whatever we're comparing x to, 1.40, and we divide it by the k value, in this case 0.0413, and we calculate what that result is. So in this case it is about 34. And so our rule of 100 is that you want this ratio to be greater than 100 in order for you to make this small x approximation. So probably x is not small compared to 1.40. But this rule of 100, the real crux is this. So if you make this approximation and it turns out that x is greater than about 0.5% of the number that you're subtracting it from, 1.40 in this case, then it was not a good approximation. So it's looking like this is not a good approximation, and we're going to need to solve the quadratic equation for this problem. So I'm not going to do all of that for you, but I'll go ahead and set it up a little bit, so we'll keep going here. So we want to get this in quadratic form. So what I'm going to do is take this term that's in the denominator here, and I'm going to multiply this term in parentheses on both sides of this equation. And so I end up with x squared equaling 0.0413 times 1.40 minus x. Now what I can do is multiply this 0.013 through the parentheses, and I end up with 0.0558 minus 0.0413 times x. So I'm going to move everything onto one side of the equal sign, and I'm just going to pick the left-hand equal sign, left side, doesn't really matter. And that's going to be x squared plus 0.0413 times x minus 0.0558, and that's all going to equal 0. So all I did was subtract this term and this term from both sides of this equation to get this result. So now you can see that we're in quadratic equation form, and the a, the coefficient in front of the x squared term, is 1. b, the coefficient in front of the x term, is 0.0413, and c, our constant coefficient, is negative 0.0558. And so using these three values, we're going to plug those into the quadratic equation and solve for x. Now it seems like we've done a lot of work to get to x, but we're not quite done yet. So let's scroll back up and remind ourselves what we're looking for. This is what we're looking for. So the question asked, what are the equilibrium partial pressures? So when we know x, we will know two of those equilibrium partial pressures, because the equilibrium partial pressure of PCl3 is x, and the equilibrium partial pressure of chlorine is x. But in order to calculate the equilibrium partial pressure of PCl5, we'll need to take 1.40 minus x. Now you may notice that when you solve the quadratic equation that you're going to get two roots. Only one of those is physically reasonable. So if you get, for example, a negative partial pressure, well, negative pressures don't have any meaning, because negative partial pressure would mean that you have 0 moles over here. All of these quantities in this equation have to be positive, and you can't have negative moles. So that doesn't make any sense. So we would want to pick the positive value to use in our calculations. And so that's how you set up the problem. So you'll need to solve the quadratic equation using your numbers for x, and then substitute that x back into this equilibrium line here to determine the equilibrium partial pressures of each of those values. And that's pretty much how most of these equilibrium constant problems go, more or less. So you need to write down the equilibrium reaction, you need to write down your ice table, you need to write down your equilibrium constant expression and know its value, and then you just substitute in, and by hook or by crook, you need to solve for x. And then you substitute back into the equilibrium line to figure out your equilibrium concentrations. So it's a lot of steps, but take it step by step, break it down, and each step not too bad. So good luck.